Today is about the use of calorimetry for quality control of cement and concrete. That's, I think, what you signed up for. If this is not what you signed up for, you might still want to stay because I think it's going to be interesting. We are actually the two we co-hosting. The two hosts here are Jeff Groh, that is the person that urged you to keep your microphones shut for now, and that is organizing all this. And Jeff is the sales manager for Calmetrix in the US and Canada, so for this North American part. And he's also the one that a lot of you have already talked to or talked to regularly when for various issues and various things that you need. And I myself am Mark Zacharias, and I'm one of the co-founders of Calmetrix quite a few years ago now. I've been with the company since day one, and I do have a little bit of a cement and concrete and admixture background that I have amassed over the years, plus having seen quite a few things in calorimetry in general. So I start to have a little bit of experience that is always good to share. And here again, I have probably interacted with some of you at least in the past. So as we look into calorimetry for quality control in general, I know a lot of you actually have already used calorimetry, probably most of you, and are somewhat familiar with it, but I'm still going to go, it's going to take about 5 minutes just to make a recap of what it actually is. And not to say that we start first with the mandatory, oh, this is who we are. So we at Calmetrix as a company have been around for now 15 years. It's a set of devices that we sell that actually found their origin in the old Grace being the admixture company that some of you know that has now recently merged into Saint-Gobain. And with Grace, there was a development of calorimeters that was a little bit in-house back then in coordination with T Instruments. That's now our competitor. And well, back then, Grace had decided to spin off the calorimetry business, and it became Calmetrix. And as Calmetrix, the company grew quite a bit. As you see on the little dots here, we're around the world. We're in about 75 plus countries. And we do have in our customer base, and this is just cement alone, we do also other industries for other things because calorimetry can be used in many different applications. And a lot of you might recognize your logos there. If you don't see your logo and you're jealous, we can add it. It's no problem. But here's a subset of our customer base, and you see that there are cement producers, concrete producers, government institutions, admixture suppliers, universities, research groups or startups that work on new types of materials and develop new things. So we pretty much we're happy to work with everyone, and it's really very motivating and very enthusing to work with all the people that are in our customer base. So I want to give you a quick overview of what calorimetry actually is. So calorimetry, as many of you know, is the measurement of heat exchange between a sample and the outside. And I think that in the last 15, 20 years, it really took off, which in the cement industry is a short time span because things are usually a little slow to develop. But it has really taken off, and there's now several standards, ASTM, EN, and others that show how to use the apparatus and that put some norms around it, which makes it easier for everyone. You in calorimetry curves, you typically see, like on the left-hand side, that you have a heat exchange in the terms of thermal power. So you have a heat flow that comes from the sample out, and that is measured as it comes out. And you typically see the speed of reaction on this, the instantaneous speed of reaction. So you see things like setting times, and you see generally how reactive a sample is. And as you can see here, you have different samples from OPC to different class C and F ashes. And you can see how they behave differently depending on the sample type. And on the right-hand side, you would have the equivalent total heat that is released, which is actually the surface area from the curves on the underneath the curves on the left-hand side. So where on the left-hand side you see speed of reaction, on the right-hand side it's more like the total progress of reaction, how much total reaction has taken place. So it's more indicative of compressive strength and things like that. But again, many of you already know all this. In terms of the different types of calorimeters, you have semi-adiabatic, which is generally an insulated box. You have like insulation around the sample, oftentimes a concrete sample, with coarse aggregates and everything, and the temperature sensor somewhere inside or around or underneath, depending on the design. But that temperature sensor will give you a temperature curve over time, and it also gives you a sense of reaction kinetics. So they're very quick and easy and generally more expensive instruments to do things a little bit in the field or for mixed designs and things like that. And that's the way they look in the real world. So we have our devices here, the FCAL, and then you have on the right-hand side the versions that are a little bit the homemade versions or coffee cup versions that some of you might have used or still use, and that work indeed for certain applications. They work. There's nothing wrong with it. And then you have isothermal calorimeters. They're a little bit more sophisticated. And those ones, you maintain the sample in a constant temperature. It's a very, very constant temperature, very much within plus minus 1,000th of a degree. And here you get you can test a sample and look at the heat release in those very repeatable conditions. It's really mostly about repeatability. And you have a number of standards that are listed on the left, and you have more in other countries too. ASTM standards and EN standards that for different applications that, again, a lot of you are familiar with. I want to just pause really quickly and ask Jeff if the sound is good.
Yes. Yeah.
Perfect.
It's much better now.
Good. So in our little world, we have of Calmetrix, we have two types of product lines for the isothermal calorimeters, and some of you have used those or are using them right now, or will be using them someday. So we have on the left-hand side our mortar calorimeters, where you can test cement paste and mortar, and that makes them very versatile. So you can use them for pretty much everything. Everything that you want to test in the world of cement and concrete, you can do in there. Some tests are trickier because you have a little bit more sample size or less sensitivity. Like typically the ASTM-C 1897 is trickier. It takes more time to actually learn how to do it. But eventually, with an apparatus that you have on the left, you can do everything. On the right-hand side, you would have the iCal Ultra, and that's more sensitive, but it's really limited to paste. So things like admixture development and robustness testing or admixture formulation, or just even sulfate optimization is like iffy because they should be done in mortar. There's a strong point to be made that cement paste is not good enough or very often can be misleading. So you have a choice between one or the other. And fittingly, the left-hand side ones, the iCal HPC version, is very often used by admixture companies or those customers in the admixture world that we have, by cement plants. And on the right-hand side, it's very often research groups in central research labs or a lot of startup companies actually like those two. But now we get to the actual topic of today, which is the quality control for cement. And when we think of quality control, we can think it in different ways. It's quite a vast subject in reality, but I would say you can boil it down to two different types of quality control that you have for a cement material or concrete or any binder that's there to substitute the cement in the concrete. So you would look at first types of quality control that's related to the product. So where you have an absolute performance target that you have for the product, such as setting time. You need the product to always reach a certain setting time. So you have a concrete mix and you want to get to a target of set time, and you test against that. So you could do a set time test with a proctor needle, like ASTM-C 403 type, or you can use a calorimeter, or you use some tool to test a performance metric for a specific parameter. And that can be sulfate optimization as well, where you have actually an ASTM standard that tells you how to do it in calorimetry. You could do robustness testing. Robustness as in resistance to small changes, like when you change the admixture dosage by 1% or 2, when you change another parameter by 1% or 2, or you change something in your fuel input in your cement plant. How is it affected? Will the quality change significantly or not? So those things you can test with a calorimeter. And I think those of our customers that use our software with the different features that are in there have seen this, and they've used the setting time tool and in the software that we have, and they've used the sulfate optimization tool on those things, and it's relatively standard and it's becoming not mundane, but something that people do readily. But the second part where we say quality control is related to the process, I think is where not a lot has been done so far. And what I think about this here is like the quality in terms of consistency, where you have the same attributes over time on different days or in different batches of a material that you get delivered. And I actually remember vividly when I started in this industry, like quite a few years ago with Lafarge, when it was still called Lafarge before Holcim. And we had a couple of plants where we were very proud of our compressive strengths. And I would go to concrete customers back then and ask what they thought about our product, and they were unhappy. Yet we had by far the best compressive strengths of all of them. And naively back then, because little did I know, I just found out by listening to those people where someone bluntly said, "Look, you can sell me rubbish every day, but I want it to be the same rubbish. I don't care so much about your compressive strengths. What I care about is like every day you deliver something, I want to know exactly what I get. I don't want to be guessing when I see a gray powder, whether this is going to work the same way as yesterday or going to be different." So this consistency has always been important. But we don't have a lot of tools, neither in concrete nor in cement, to do this easily and on an ongoing basis. And so I think calorimetry is actually a good tool that can be used for this. And it's a tool that has been around for a while, and we had actually introduced in 2017 a software feature for that. And as many things, it takes a little bit long for the industry to latch on. But as of late, we've seen more interest, and actually a couple of papers have been published talking about this. And it's become a little bit more fashionable. So I think it's the right time to revive it and show people that it exists. And that's what I want to do today. So first of all, for when you want to do proper QC, what type of calorimeter should you use? What can you use? So we said we had the semi-adiabatic and we had the isothermal. The advantage of the isothermal being the repeatability. When it boils down to it, things like set time, robustness test, you can do with the semi-adiabatic. And I say this, I insist on this because yes, the semi-adiabatic is cheaper, and somewhere you have to understand why you pay more for an isothermal. But things like optimum SO3, consistency, or even many of the other things, you do need the repeatability that you get with an isothermal. So when it's all said and done, I just believe if you're serious about QC, you just need excellent repeatability of your test tool. Because at the end of it, you do not want to be guessing when you have a difference between your sample that you took yesterday and the sample you took today. You do not want to be guessing whether this difference is due to external conditions like the different temperature, different curing the conditions or something, or whether it's due to the actual sample. And to take the doubt away and make sure you compare apples to apples, you will need this isothermal calorimeter. Yes, it's more expensive, but I'm not here to sell. I'm here to actually suggest what the best tool is. And so if you look at those just quickly one by one before we get into the actual thing that I think is of interest today is the quality control as related to the process. For setting time, and those who have already used this know it. So in our software, it's the way the software looks. You have different tabs here you can click on for different functions, for to do reports and visual analysis, for the compressive strengths, for sulfate optimization. Here's the QC one. That's been there for 2017, but was largely overlooked until just recently. And then we have the setting time, the heat of iteration, et cetera, et cetera. So for setting time, you could, for example, here you have a target setting time, and you could think about this is actually a case where you use different grinding aids or performance enhancers, and you want to look how it affects the quality of your cement when you use one versus the other, and then you have a certain target, and you can easily assess how other dosages and how other types of grinding aids that are supposed to be equivalent will affect the setting time. So it's a good quality control tool, both visually from the perspective of a qualitative assessment, as well as quantitative, because you do actually have estimates of initial and final set here on the bottom. So that's a good tool for that, and a lot of people have used it, so it's not so new. Sulfate optimization, the same. We actually have a ready-made software for that. It follows like the standard, the STMC 563. You do a few samples with different levels of SO3 in them, you get those curves there. It's actually all of this is the same cement. The only thing that actually changes is just the quantity of sulfate in it, and you very quickly get an assessment of what the optimum would be. So the software spits out the optimum. It's really an easy to use tool compared to anything else that you would do. It's easy to use in absolute terms, but even more so if you say compared to doing strength cubes and everything. So it's quite easy, and it's become also very common to use this, and many of our customers use it. Not only cement companies, by the way, also admixture companies, etc. And then robustness. Robustness is also something that's visually very easy to interpret. Here's an example of an increasing the dosage of a water reducer in a concrete mix, and as you increase the dosage, every time you increase by a certain amount, you see that the curve shifts to the right, so the setting time gets higher and higher. And it's quite a linear response to the dosage. So you can see, you can look at your robustness in a way, okay, if I'm off by 1%, how much does it affect the setting time in percent? And you can also see that at some point when you overdose, then you just kill the mix. That's the pink curve. So you can also find your limits. So here again, it's a very, very easy tool. And another example, this one on a semi-adiabatic calorimeter is, for example, if you have ever wondered how different is it when I use my mix with the reclaimed water in green versus the same mix with just tap water. You know, when you have those concrete reclaimers and you sometimes you reclaim the water, yes, there's some residues of admixtures in there, and it does change things. And you can visually assess the robustness by changing the type of water that you use in your concrete mix. And again, it's very easy. But as I said, these are things that most of you have probably used, that most of you have seen, that are common. What gets now a little bit newer and more interesting is on this consistency part. And when we look at the consistency, we have precisely this one tab, this one QC tab that helps you do this. And this is what this, if for those of you who've had the software and that have used it before and have wondered what this is for, this is what it looks and this is what it's for. So what you normally do is that pretty much every day or every week or every month, periodically, when you want to look at the consistency of your production, whether that's concrete or cement. For example, if it's cement, it's a continuous process. So you could say, well, every 2-3 days, I take a sample and actually make a calorimetry curve. And every time I have this curve, I will put it in here. I can look at it. I can look at different parameters, which I will go through. And then I can add it to what we call a data set. It's actually a small database of those curves. And I can look at different parameters, which I will go through in a minute. And I can see how they evolve over time. So I can see a trend line. I can see how things evolve over time, and that tells me a lot about consistency, because well, trend lines that have a heavy slope and things that go up and down like this are not very consistent. You could do this, of course, as I said, for ordinary Portland cement production, for the production of another type of process that's a cement substitute, whether it's the ones that use alternative kilns that use less power or no kiln at all, that do it through chemical process. If it's a batch process like concrete, you can do it. We have a few customers that have done this on large projects. Like I'll show you later an example of a company, a concrete company that was batching every day for a dam project, and they were taking a sample every day to make sure that it's consistent. So it can be done for any type of product that gets produced in our industry. And the way we look at this, we try to characterize the curve by a few points on it. And based on our experience, because we're all guys that come from this world of cement and concrete, we have defined a few of those points. So there's nothing universal about those. There's nothing about that comes from a norm or a standard. It's still an open book. So if anybody, for example, in this crowd of people today, were to come up with something that's a good idea or better, that can always be added. But for now, we have a few points there. I'll show you what they are. And these are the ones where we look for consistency on those points from one curve to the next. So here we have a typical cement curve. It's a Portland cement curve over the first 24 hours. And the first thing we look at is where the reaction actually starts, where it begins. And this is a particular point. We actually have a definition for it. It's the intersection of the tangent that comes from the inflection point where it intersects with the lowest power. But that's a lot of jargon. What it represents, it's where the reaction takes off after the dormant phase. You have the dormant phase where not much happens, and then all of a sudden it takes place. Like hydration starts, and it's like the beginning where it starts to get to work its way towards the initial set. So it's not quite initial set yet, but it works its way there. And by looking at the time when this happens, where the beginning of reaction happens, and the power value, the thermal power value at this point, we have here a consistency parameter where we can look how this varies over time. The second one is at the inflection point. The inflection point is also interesting because in this curve, since it's the speed of reaction, it actually shows you where the reaction goes from accelerating, where it goes faster and faster and faster, to decelerating. So it's also indicative where like the final set is about to occur. Not exactly the final set, but again, it's a very convenient point on the curve to look at to understand how this evolves in the terms of consistency. And then the next one is the peak of the thermal power curve. And that one is interesting because that's the maximum speed of reaction. This is a speed curve, remember, it's instantaneous speed. So this is really where the molecules in there are the most active and the fastest in combining before they gradually do it slower and slower. But this is really the peak value of the speed, and you do want to know at what time that happens and what the highest power is. If the power is very high, it means higher speed, so very reactive mix, very reactive. And if this occurs very early, then it's a very fast mix in general, in terms of everything. Every performance parameter will happen faster. And then finally, we look at what's called the onset of sulfate depletion. So those of you who have looked at this sulfate balance a little closer know this very well. This second peak here, this bump here, is a sulfate depletion bump. What it means is that here you have B-light reaction going on, reaching the tallest point of this peak, and the B-light reacts, and that's good because B-light is what's like strength gaining. We want this to react. And while B-light is reacting here and is hydrating quite happily, at the same time we have the sulfates that keep our aluminates in check in the cement. They keep them harnessed so that they don't steal all the water away and don't hydrate yet. That's why we add the gypsum to the clinker, right? So we have this, and by the way, this I talk about this with Portland cement and everything. But if some of you work on LC3 on the limestone calcined clay cements, sulfate balance is also very important. So it's very similar. You also would look at this. So here and here at this point where you have sulfate depletion, it means there's no more sulfate here. So it means the B-light basically, that's it. The reaction is cut short. And here comes the aluminates, they come back with a vengeance, and they all react because there's no more sulfate. So this is the sulfate depletion point. And we look when this happens, then we also look at how much time there was between the main peak and the sulfate depletion, because you want to give enough time for the B-light to finish reacting. And as per ASTM C563, this metric here is actually an excellent indicator of consistency. When you keep this pretty consistent over time, and how do you keep it consistent? You keep it consistent by manipulating your sulfate content. Then you're assured that you have a good, consistent product. It's a very good metric for that. And then finally, on the total heat curve, we also look at the total heat that is reached at 24 hours, maybe at 72 hours, or actually at the time you want. You can define the time you want. You say, oh, I want to know at 36 hours. You could do that. But you do want to know and benchmark this from one curve to another. And when you do all this, you get something that is quite an easy process, actually. You take a sample at regular intervals, once a day, a week, a month, whatever makes sense. And then you run a calorimetry test on it. You could do 24 hours, 72 hours in general, because all those points, most of those points are in the first 24 hours. 24 hours is actually enough if you look at a cement or concrete. And then you can add each new curve that you generate to the data set. And then you have data analysis. Quite easy. And the way this looks, I'm going to share another screen so you can have a look at the software actually. Okay, so it's going to take just a moment, and here you go. So almost there. So if I share this, I assume you now all see the software. If you don't, then just someone shout out that you don't see the software. But this should see a screenshot of software that shows a bridge. It's actually a bridge in Boston, the Zakim Bridge in Boston. And you have all those different tabs that I showed you earlier, and I said we're going to concentrate on the QC tab. So to show you live how this works. So let's say I'm doing today I'm doing one of those tests. I take a grab sample from a cement production, and I load here a log. And I take this log here. This is actually from 2017, so it's a very old one, and it's from a plant in Canada. And that's the way it looks. It's the curve I had before. And here you can see how we will look at the different parameters. If you click here on the T begin, it'll show you this little cross here and says, okay, the T begin here, where the reaction actually begins, it's 1 hour and 26 minutes. And it has an equivalent power of 887.13 microwatts per gram. That's how it is. Inflection point, the peak. Sometimes the software can actually go wrong if there's lots of peaks. It can select the wrong peak. You could actually move this manually if you wanted to. But in general, the software is quite good. It's mathematical. It's quite good finding where those peaks are and those things. The power of the peak, and then where the sulfate depletion occurs, and then on the right-hand curve at 24 hours, what the total heat is. So I have one point here, and I can actually just add this point and create a new data set. So now I create a new data set here. And then if I have another point that's from the following day, it was grabbed on the 17th, then I put my grab date here, because the grab date is not necessarily the date when I actually tested. I might have grabbed things over a week and then test them next week. That all depends on how I organize myself. But so this is the grab date, and then I say, okay, I will add this point. And now I have 2 points, and I can go on and on and on. Don't worry, I'm not going to do them all. Just want to have 3 there so it doesn't look as goofy. And then I add that point. And so now I start having like a trend line. Of course, with 3 points, it's not enough to be really meaningful. But when you do this for a little while, you actually have quite an interesting set. So I have a few here that they're all from real examples. So we can't really make this up. We really need something from production. So there's from customers, from different customers that graciously gave us their files, and so based on being anonymous, and we have them here. So I can load this set from this plant in Canada, and that was here, and that's how it looks over time. So here, if I look here, for example, I look at the time of inflection. So what does it tell me? So it trends upward over time, but it goes up and down. It's kind of hard to assess whether that's a big deal or not. I have to look at the scale. I can say, okay, it's this time of inflection point, which is, as you remember, it's the point here somewhere where the reaction goes from accelerating to decelerating. That's sort of indicative of where my final set is close. And when I look at this, then I see it's somewhere between 4 hours and 4 hours and 45 minutes. So it's okay. It's within 45 minutes. It's not that bad. So I see a trend line, but I could see a trend line for example, the power of the peak. Right? And as I see this, I can start retracing it and try to say, okay, so why does it peak up here in this period during this week? So maybe I changed to a different type of fuel, or I changed something in the kiln that changed its temperature, or I changed something in the mill, in the grinding process. I'll be able to sort of trace it back to changes I did in the process. And while looking at this graph is sometimes difficult because it's up and downs. And with that said, as you have more and more data, you see a better trend line. If you have a data that are over several weeks to several months, you start seeing really, really nice trend lines. But you also have on the bottom here, you have the statistical data for each of the parameters. You have, for example, if you look at power, where the reaction begins, in this case, you have a mean value of 793, that's microwatts, a maximum 887, minimum standard deviation, and more importantly, you have a coefficient of variation. For those who are not familiar with it, because not everybody maybe knows, but coefficient of variation is the standard deviation divided by the average. And it's expressed in a percent. And a percent like 7.4 is not good, but it's not horrible. If you, for something that's really tightly quality controlled in general, not just in cement, you would be less than 1%. But honestly, in cement, I have not seen a tight control like this on some of those parameters. Be less than 1% is almost impossible. It's almost easier to do in concrete. But for each of those, you have those different parameters and those different statistical values. And you remember, for example, that I said that in ASTM C563, they tell you that the time between the main peak and the sulfate depletion peak is a very good indicator of consistency. Well, what we see here is that 26% of coefficient of variation means that this cement in this phase of production over 2 weeks was not very consistent at all. It wasn't that good. There's a reason for that, because they did implement changes precisely in those 2 weeks, and we're monitoring those changes. So it's not like this plant is not always bad at maintaining a consistent product. The impact of those changes precisely fueled the inconsistency. And I want to show another example of this, of a similar set from a concrete project, from that dam project that I mentioned earlier. So I'll load this set, and this was from a dam project in Brazil. And here, this looks as dramatic as the other one, but actually not. This is actually much better. They really maintained the concrete pretty tightly controlled. It's just from the scale that's here, it looks dramatic, but in reality, it's quite nicely maintained, and you can see it here in the coefficients of variation that are like 3.12% for the time of SO3. That's really good. For the power of the peak within 1.31%, that's really tightly controlled. And this is for, so it was for dam project where every day they would batch a new batch of concrete with the plant that they had on site and use that batch in the morning and then only pour in the morning. And they would take over the course of a couple of weeks, they would take every day a sample and look at this way. So once you have this software tool, and once you have a curve that you add every day, it's quite easy to follow up on the consistency of your product by just doing this. So that's what the software looks like. Now I do want to go back for one more thing. I think we'll be able to open up for questions. I will go back to my main presentation here. Okay, so now you should see my main presentation again. I'm going to go back in slide mode. Okay, so this is basically what I said from before. You have a current curve. Now summarizing the current curve, you can add to your data set of existing existing parameters for the curves from other days, from the days before, from other instances. Could be a few on the same day. And then you're able to visualize trend lines for each of the QC parameters here, and that you can pick, and you're able to visualize statistics like the mean value, minimum, maximum, standard deviation, coefficient of variation, and it gives you a pretty easy way to assess how consistent your product is and trace it back to certain events. Of course, the software does not do this automatically, but if you somewhere have a logbook of things that you did on certain days, you'll be able to understand why those changes occurred, like they did in this particular example from that Canada plant. Okay. And then I wanted to show you that, because here we have things where you have to trace a 24-hour curve and wait for 24 hours to actually get a result. The main reason is that even in an isothermal calorimeter, the repeatability is not good enough to do it quicker, because theoretically you could say that just with the illuminate peak you have in the beginning, the first 30 minutes, you should be able to see if there's a difference from one peak to another. But you don't get that level of repeatability, even in a just plain isothermal calorimeter, to be able to do that, to see in half an hour of reaction measurement if something has changed or not. But there is an apparatus where you can do that. It's like this robotic apparatus that you see here. Automated and here you can see it on the right-hand side. I hope the video is somewhat fluid.
Yes.
Where the robot actually does all the sampling, so it's the exact same sample procedure each time. The mixing is like flawless. Everything is to perfection. So you actually get curves where just with the illuminate reaction, you can look at it and you can have good quality control, like actually excellent quality control. It's For cement production plant, it's actually interesting because it's quasi real time. In 30 minutes, you would see if something is affected, and you would be able still to make changes in production that are meaningful. Because otherwise, if you do the changes in production tomorrow, and you already have produced a bunch of cement that's stored somewhere and that wasn't necessarily very consistent. But this particular one here just helps you to do this in the best possible way. And with that, I come to the end of what I wanted to cover, and I think we have 15 minutes left for questions if there are any.
So Nick, go ahead.
Yeah, so early in the presentation, you mentioned when doing the isothermal calorimetry that it's better to do a mortar mix instead of paste. Can you
Mhm.
expand on that a little bit as to what the benefits are there and maybe what mix should be used?
Sure. So it basically it depends on what you want to test. So if you test, the rule of thumb is if you test anything that has admixtures in it, you do want a mortar test. And quite frankly, it's not realistic to think that any concrete or cement today is used without admixtures. So it's a good idea to very often test with mortar. And the reason for that is because many admixtures, the majority of the newer generation admixtures, actually are sensitive to the mixing energy. And the mixing energy you get just with paste when you put this together is completely different from what you get in the real world when you do concrete or mortar. Mortar and concrete is similar. So that mixing energy has pockets of heat that are localized and that make the additives react very differently. And it's to the point that when I worked on admixtures a long time ago, we had issues with this because we were doing paste calorimetry and we had literally results that were completely opposite to the reality in the field. And to recreate that, you do need mortar. There's actually even publications that have published things that are wrong just based on this mistake until people found out. So to be safe, when you want to test things to be applied in the real world, it's mortar. If you test things where you just say, I theoretically want to look at reactivity of a material, of a new binder maybe, and first I do a bunch of testing to just get to a binder that seems to work, paste is fine there. But in the final test with admixtures, it's always going to be mortar.
And for the mortar, do you do a set mix every single time of ratios?
So it has an advantage. Depends when you're within one single matrix, a testing
Yeah.
matrix, where you test like several formulations and things. You do want to keep everything else constant. So you want constant air, the same ratios of you want to use a standard sand, same ratios of aggregates to cement, of water to cement, etc. So keep everything constant. It doesn't have to be a mix in particular, but every time you want to compare apples to apples, you want to keep most of the things constant except what you want to test.
Okay, so you're not going to use anything like a normal consistency, anything like that
You could
to help
too. It
determine.
will really depend on the type of test. You could also base it on normal consistency and keep that constant every time. It
Okay.
will really depend on the type of test, but you just gotta. It's design of experiments depending on what you're after.
Okay. Thank you.
Mm.
All right, next up, Anika, if you can unmute yourself and ask your question.
Yeah, just for clarification, you mentioned that the inflection point was representative of the final set. I was wondering if you meant the initial set.
No, I did mean the final set. So actually, traditionally in the olden days, 25 years ago, people were very happy with looking at calorimeters and say, "Oh, I got it. For initial sets, it's easy. We're just going to take the maximum acceleration, which means you take the third derivative and you look when it zeroes out. This at the beginning when just it starts accelerating at the max, and we take the final set as the inflection point, which is taking the second derivative and seeing when it zeroes out." But when people did this, it became actually very difficult because those curves are not as smooth as they look. And when you take the first derivative, they're less smooth, second even less, and the third is like total chaos. And so it didn't really work. But indeed, you think about initial set usually as the maximum acceleration, and in the final set, it's where the inflection point of the speed curve is. So from where it goes from accelerating to decelerating.
Okay, does that answer your question, Anika?
Yeah, thanks.
Mark, there's a question in the chat from Prasad. Does isothermal calorimetry pick up influence of illuminates from slag on the sulfate depletion peak in blended cements?
Oh, very much so. It's actually it's extremely visual when you have a good looking cement, actually the one that we have here is a good looking cement because it has its sulfate depletion peak a few hours after the main peak. It looks great. If you put a slag in this that has high aluminate content and it consumes all of the sulfates, this peak will go, it will move to the left. Sometimes it happens before the main peak, which is, it's super visual and very easy to correct and very easy to optimize. Very easy to optimize when you add a little bit more sulfate again. You can see it move to the right again and re-optimize it. So the answer is yes, and it's very, very easy and visually easy to interpret.
There's another question mark, Muhammad. How could we know that the sulfate depletion occurred before the peak from the graph?
Okay, well, you would see a bump before the peak. I wonder if I have a curve handy for that. I'm not sure I can find one so that quickly.
In the case that it's under sulfated, I guess is the question.
Yes, it's under sulfated. So well, I don't have this specifically. I can show a few other ones that doesn't exactly answer the question, but it'll show you how you spot the sulfate depletion peak at least. So let me just show you some here that I happen to have open. So this is in the sulfate one. Here you see this is the same cement. Here you see the peak is pretty close to the main peak. If generally when it's before the main peak, it's just flat. It's like one single peak. And then if you look closely, you see a little bump before, but sometimes not even that. But if you see just like one peak like this, that's just not the double peak and nothing after that, just like very smooth, then it means it's before. Here you see this is like as you add more sulfate gradually, you have 2.43 sulfate percent of SO3. It gives you this. When you add a little more, you see this move to the right here. That bump moved to the right. So that sulfate depletion is quite a lot after the main peak, which is fine. And here it moved even further. You can see it here now. And then as you add more and more and more, here you don't see it anymore. So it's I actually do see this here. So you have to follow the curve, or you have to use the software. The software will find it for you. But without the software, you would have to follow the curve. And if you don't see any bump after the main peak, then it means it's before.
Okay. Our next question mark from Muhammad is, and both Angel and Mujtaba, I will reach out to both of you on your questions, but a question from Muhammad: what is the minimum energy generated in joules per gram as per ASTM for OPC?
I don't think that there's like benchmark values. There's benchmark values from different round robin tests and everything. So an OPC will generally give you, and you have to say at what curing it is, 72 hours or 7 days, or at 7 days it will get you to 320 joules per gram. That's like a pure OPC. But then it depends. Limestone cements are different. 1L, 1P, they're all different. But I'm not aware. That doesn't mean it doesn't exist, but I haven't seen any ASTM standard that actually mentions a minimum that to make it qualify as a Portland cement or something like that.
Okay.
I wouldn't know.
Yeah. Okay. Yeah, we get those questions from time to time, and it's hard to answer those. Let's see. I see
See
somebody's.
for iCal 8000, we have remove the cover every time to load a new sample in.
I think what he's talking about, I think probably that question has to do with the silver cover on top of the instrument mark.
Yes.
Yeah, it's that question, which also comes up from time to time in terms of whether that could be hinged or a simpler way to get in. But I think that's Rotana, correct me if I'm wrong.
Okay, yes, sure. Cells. No, we have not. I'm aware, of course, that you get a bump when you do this, but these disturbances, while cosmetically they're unappealing, they really have absolutely no effect on either the reaction of the other samples or the interpretation that you could get. So for practical matters in this particular instrument, it's a deliberate design choice to make it this way because the results are unaffected by this bump, and not having it would convey other disadvantages from the design perspective. So it's like a trade-off. In the other instrument, in the iCal Ultra, you have a means to actually do this individually and there's also specific reasons for that. And here, yes, you look to minimize the appearance of those bumps because the sample size is smaller and the relative size of those bumps has a larger influence on the sample size. But for the large sample sizes you have in the motor calorimeters, like in the iCal 8000 HPC, it would not be a wise design choice overall to do this. That's the answer. And the reason that if you want more on that, Rotana, you can of course reach out to me individually, and I'll explain all the real reasons behind all this.
Okay, let's move on. We'll get to everybody's question here if you just be patient with me. But Jeff Hook, go ahead. You raised your hand a while back, and go ahead and ask your question.
Or I guess it's just a question on the screen. So do I see that mark correctly, that at the bottom that I can look at the optimization age? So that's one of my struggles with isothermal in general is, so I can actually do 24 hours, 28 days, however long I run it out, and it will draw the curve for me for the optimization based on that time.
Yes, that's right. So, for example, here we have a curve that goes all the way to 168 hours. But truth be said, the sulfate optimization for cement is done, and it's all done in 72 hours. The sulfate level to maximize the performance at 72 hours will be the same as 28 hours. And the reason is because pretty much 96% of the reaction is taking place in the first 72 hours. The rest of it is just like it's physical. It's
Yep.
the strength scaling is based on the porosity and everything. But so measuring 72 hours is generally enough. So this particular user has measured 168 hours, but it's not needed.
What about setting? Do you have software to be able to optimize for like the initial set and be able to optimize that way as well?
We have software to try to assess it, to measure it, to look at how much it could be, and it's the setting time software here. But to sort of find how to optimize it, no, we don't have that.
Yeah, I meant as a function of sulfate.
No,
Okay.
because why is that? Because we actually have not seen a correlation between set and sulfate as such. So there is a relationship between the two, but it's not a correlation mathematically. Whereas it's well established since 1948, since a paper published by a guy named Lurch, who basically back then said to optimize sulfate, you can do you have three methods. You can do shrinkage, strands, or you can do calorimetry. But 1948 calorimeters there was nothing really available. There's no electronics. It was very difficult. So that the easiest is strands, which is not easy at all. But it's really those correlations that have been established. You can do it through shrinkage, strands, or calorimetry. But I have not seen anything that actually correlates it to set directly.
Okay, thank you.
Okay, Mark, next question. We got three more questions in the chat. Luke asked, and it's kind of related to the previous question, but how do you interpret curves when the sulfate depletion peak overlaps with the maximum peak?
So here again, so what you will see is like just a smooth curve without anything. And I regret that I don't have any. Then again, this one was not exactly a topic for today. But if you reach out to us by email, I'll get you a curve where it actually shows exactly that. So what you would see is just like a very smooth plain peak with no bumps after the peak. So you have to look all the way until 24 hours after the peak. If you see that the curve starts changing its slope abruptly, that's like the sulfate depletion bump, and that's the way you would spot it. When you actually see a few and see them side by side, it'll become way more obvious than what I'm saying here. Unfortunately, I don't have any handy like that, and I don't want to have everybody wait for 15 minutes to find one.
Yeah, Luke, you can reach out to us and we'll get that resolved for you. Alexander is asking, it's a long question here. Let me see if I could. So with adiabatic, developing a method for set times and using Thermocal 2, we have been instructed that a good general rule of thumb for the initial and final set fraction is for 2/3, or refer to ASTM 753, which cites values 0.21, 0.42 is this rule. So yeah, so Alexander, yeah, the rule is still applicable whether it's on semi-adiabatic or the isothermal. You know, the rule of thumb that I typically will show people how to use that because it's the simplest is is a great tool for comparing sample A's to sample B, and it's applicable to both the semi-adiabatic and the isothermal in the case of, and in both cases, whether it's semi-adiabatic or isothermal, you also have the option of creating an empirical model where you take a standard mix design, standard mix, you run the calorimetry, you do physical set time testing, and then correlate and create a model that gives you the fractions based on empirical modeling. So that's the other option, the 1/3, 2/3, or the 0.21, 0.42. Those are different rules of thumb that various folks in the industry use. They're pretty robust. I mean, the most important thing on those rules of thumb is that you use the same one over and over again. You don't switch between the two of them. Probably more important. So yeah, it applies to both instruments. Mark, any other insight or question or
Yeah, well, that 1/3, 2/3 is from years of experience, and ASTMC 7053 has others because it's written by someone else who also has years of experience. None of them is bad or good. The reality is, as those curves, when in the ascendant phase where the curve goes up before the main peak, the steeper it is, the more irrelevant it becomes to argue whether it's 0.21 or 1/3 or something like this, because when it's quite steep, a slight change in the ratio will not induce a lot of change in the time. If you look at a very steep curve, you can be quite wrong in the ratio. It will not change a lot on the x-axis in terms of time. So just to add that to it, that the 1/3, 2/3 is valid for plain Portland cement or something else that's quite reactive, or limestone calcine clay cement, but not something that's like loaded with fly ash with a curve that's relatively flat. There you have to be careful with using this rule of thumb because it's less valid when the curve is quite flat. The steeper it is, the more valid it is.
Okay, and then let's see, Ratana has got another question here. Why do we call a sulfate depletion peak, as sulfate is mainly consumed during hydration of C3A, which happens after the sulfate depletion peak? Question mark.
You're putting the finger on something that exists in this or in other industries and things where people call something a certain way to vulgarize when actually the chemistry aspect is more complex. And I get, Rotana, that you're well versed on the chemistry aspect. So I didn't coin the term sulfate depletion. I think the reason why people came up with the sulfate depletion is that you initially put sulfate you mix it with the clinker to avoid the aluminates from reacting too fast. And what they mean by sulfate depletion is they mean that the level of sulfate has reached a point where the aluminates are no longer controlled by it. And so if I had to call it today, based on your comment, I would call it the aluminate recrudescence peak, and something like this, but maybe not the sulfate depletion peak. But it signals what it's meant to say. It signals the moment where aluminates actually come back and react in the detriment of all the other phases.
But I appreciate all of you coming out, and you know where to find us. And we'll be following up with a recording of this webinar as well. So thanks a lot, folks.